We already know from last semester what it means by saying xy has joint cumulative distribution function fxy. It means for all xy in R, fxy means probability that capital X is less than or equal to x and y is less than or equal to y. In other words, if xy is a point on the plane, in that case this means you are considering the region to the southwest of this point, the infinite rectangle, and trying to find out the area above this under the density surface. Of course, this definition uses just CDF, so it is perfectly general. It does not care whether you are working with discrete or with density or whatever. This is a general definition, but when you are working with a joint density situation, then it amounts to finding the volume under the density curve above this infinite floor. Thus, finding the joint CDF amounts to finding a probability, so we can either use geometric considerations for simple cases or we can use iterated integrals for more complicated cases. I will show you one example how to compute the joint CDF from the joint density using just geometric concept. I have given xy with joint density this, which is basically uniform over the unit square. I have to find the joint cumulative distribution function capital Fxy. So let's first think of it pictorially. This is the xy plane. So for every point xy, I have to find out the value. Now the entire drama takes place in this unit square because xy can take value only here. So with probability 1, it must lie here. Now what I will do is I will partition the entire plane into a number of parts. 1, 2, 3, 4, 5, 6 and 7. For some of these parts, it is very easy to work out this thing. For example, what is capital Fxy? If xy is this point, all that I have to do is to consider that infinite rectangle to the southwest. What is the chance that xy lies here? 0, because xy cannot lie anywhere outside this square. So all throughout this the value will be just 0. Okay, let's see what is the value here. If I give you some xy here, in that case what is this? It is the probability that the random point x comma y lands in this infinite rectangle. And that is certain because x comma y must be in this square and this square is inside this infinite rectangle. So it is a certain event that xy will lie in this bigger infinite rectangle. So the value here will be 1. What will be the value if xy is here? Again, you imagine this infinite rectangle. This infinite rectangle does not overlap this. So here also the value will be 0. Similar argument shows that here also the value will be 0. Let's erase these ones. So the only places where you have to find this are over these 3 places. Okay, let's try this one. What is the probability that your xy lands in this infinite rectangle? I know that xy has to land in this square. I also want to land it in this huge infinite rectangle. So xy must be in this rectangle. Now I am working with uniform distribution, so I can use that area by area formula. Since this point is xy, so this rectangle has height y and base 1, so the area of this rectangle is y and the area of the entire square is 1. Therefore, I can say that it will take the value y in this region. Similarly, if I take xy here, then my point has to lie in this rectangle which has area x because this is x and this is 1. So over this region everywhere my fxy will be equal to. Now all that remains is over this unit square. So I pick some point x comma y over here. Then my point xy will lie in this infinite rectangle, means it has to lie over this rectangle, and this rectangle has height y and width x. So its area is xy. Xy divided by the total area of the square, which is 1. So the value of fxy over this square is x times y. So we have obtained capital Fxy and it is given by this. Of course, I can write it as Fxy equal to this, if this, if this. So I can write a long set of clauses because there are 7 parts. There will be 7 if clauses. But it is easier to just write it in this pictorial form. Now this is how the 3D surface looks like. I have taken this from the class web page. So this is the unit square and it goes on 0, 0, 0. It is moving like x and y and this is always 1. And this part is xy, so it may not be apparent, but there is non-linearity here. There is a curvature. It is sloping down. So that is how it will look like. Now in this exercise, I ask you to do exactly what I have done, except that I have changed the density from 1 to x plus y. So simple geometric considerations become a little bit more complicated. So what I will want you to do is to find out some of these cells where the values remain unchanged. So out of these 7 partitions, some of the values will still remain unchanged and only some of them will change. Out of these, one will be this cell. So I want you to find out which cells are going to change and work out the value for this cell only.